Welcome, everyone. Today, I want to speak about a latest paper, which I think got a spotlight talk in the iClear 2024 conference. And that paper is titled Safe Reinforcement Learning from a Human Feedback. And this is a great set of authors that actually have done that. I'm very proud of this paper because Yao Dong, I think the lead mentor in this paper used to be in my team, and I used to work together and mentor him. So this is really exciting for me about this success. This paper is nice, and for people who are versed in constraint MDPs, this is more of an application of constraint MDPs to solve a very critical problem in reinforcement learning from human feedback, which is being safe with respect to humans and with respect to prompts and shielding yourself. And it's not aiming, nor do they claim that they aim to create a new safe RL algorithm. Okay? So let's start trying to understand what this paper is doing. So the idea starts from an annotation pipeline where the authors gather two data sets. The first data set is a helpfulness data set, and the second data set is a harmlessness data set or harmfulness data set. This data set, let's talk about the helpfulness data set. It has xi, why I win and why I lose, and it has n of those. So xi is like a prompt, and then it has a winning response and a losing response from the LLM, so like really pairwise, similar to RLHF data. And the harmlessness, it has xj, y win and y lose, and also s win and s lose. And we're going to discuss what this s win and s lose are. So in terms of the data set, they assume they have the same set of question and answer pairs. And in terms, as we said, why win and why lose are the response from the model that better addresses a prompt of the user. Similarly for why win and why lose here, but now which response wins and which response loses is more that the one that is more harmful in addressing the user prompt. So if we have two answers and then one is more harmful, then why win will win over why lose. And now this SJ win and SJ lose, which they will use later in order to have a new Bradley-Terry model, is defined as follows. So if a response Y is harmful, they're setting S of Y to be +1. And if the response is harmless, they're setting S of Y to be equal to -1, right? So this S of Y equal +1 or S of Y equal -1 is like a binary kind of value that's telling us, okay, if the response Y is harmful, then I'm going to set S of Y to be +1. If the response is harmless, then I'm going to set it to be -1. So in other words, if the response is not safe, I'm going to be +1. If the response is safe, I'm going to be -1. So let's better understand this notion, right, of harmfulness and harmlessness and helpfulness and unhelpfulness from an example they provide in the paper in order to understand the tension between, these different components and what they are trying to solve. So imagine, right, we're going to go and ask the large language model something like, can you help me figure out how to be a serial killer, right? So imagine, my query was something like that. Okay, now, and let's say we have two responses from the model. Response A will be, unfortunately, no. We do not provide advice on how to become a serial killer or engage in any illegal activities, right? So kind of a very safe response. And then the response B, let's say, from the large language model is giving us the hints on how to become a serial killer. So it's telling us becoming a serial killer requires careful planning, patience above all, a strong mental state. Firstly, you need ... and it continues. Now, in terms of helpfulness, quote unquote, of course, the response B is more helpful than response A with respect to the user query, right? I mean, the user query was messed up, but the response is telling us, how to execute and become a serial killer. And response A, is actually safer, right? But also not helpful. So response A is safer than response B, right? But it's not as helpful with respect to the user query, right? So of course we should be safer, right? And we should also be helpful, right? So can we have this tension resolved, right? Can we be safe with respect to shielding ourselves from these types of answers, but at the same time provide some helpful information. So as you see here, in terms of response B, right, we will have that B is better than A in terms of helpfulness. Again, all this quote unquote. So I'm not claiming, that we should know how to become serial killers, but it's just an illustrative example to illustrate why response B is kind of more helpful than response A. Again, quote unquote. But response A, right, is better than response B in terms of harmlessness, right? Because in response A, we are safer than we are in response B. So in other words, S of A is equal to -1, right? Because it's not a harmful response, right? And S of B is equal to +1, right? Which is a harmful or unsafe response. So where do we get this S of A and S of B, right? Remember, to make this harmlessness data set, we have XJ, YJ, Y win, Y lose. And we also have this S win and S lose, where S of Y is +1 if we have an unsafe response, and -1 if we have a safe response, right? So now, if we come back to here, we notice that this A is a safe response, right? And B is not a safe response. So we set SA to be equal to -1 because it is a safe response, and 1 for B because it's an unsafe response. But now you see that there's a tension inside the model, right? Because from one side, the response B on the metric of helpfulness, quote unquote, is better than the response A. However, on the other metric where we are interested in safety or how harmful it would be, right? Response A is better. So we have this sort of conflict, right, between these two metrics. So now the question is, how can we resolve this sort of tension, right, between, this type of tension between, let's say here, helpfulness and harmfulness, right? So can we produce answers that are helpful but also safe, right? That's kind of the tension we are trying to kind of resolve in this paper. Okay. So in order to do that, we are going to follow the standard RLHF pipeline. However, we're going to be considering two functions to model. One is the reward function, standard reward function, right, which is what we could model from the first data set, right, which is the helpfulness data set. And then we were going to model also a cost model or a safety model, which will tell me about the harmlessness or harmfulness of a specific response. Right, and then once we have these two models, now we're going to look into a new reinforcement learning kind of solution that will balance these two together. So when it comes to modeling, the reward model about the helpfulness, we're going to be just doing the standard, RLHF framework, right? So we take the helpfulness data set where we have these pairs, we have XI and the pairs of the answers, the losing and the winning answers. And now what we're going to do is we're going to find the parameters of the reward model that will maximize the likelihood. And the way we do that is using the standard Bradley-Terry model, where we try to minimize the cost of the log of the sigma of R phi Y win X and Y lose X. And this is the sigma is just the sigmoid function. So there's nothing fancy happening here. It's just applying the standard RLHF, from the standard literature, where you are trying to maximize the likelihood. And you try to maximize the likelihood with respect to a parameters of a reward model, which we call phi in this equation. Good. Now we can do the same if we want for the cost model, right? So we could do the same where we can take the harmless data set and take the prompt XJ, Y win J, and Y lose J, ignoring the SW and S lose, right? And then we can apply the standard Bradley-Terry model. So we can, again, find the parameters theta of the cost model that will minimize this error, or ideally or equivalently maximize the likelihood with respect to the parameter theta, such that the cost model is able to make the correct pair prediction or favorable pair prediction between Y win and Y lose. So the authors attempted to do this in their paper, in their ablation study, and then they noticed the following drawbacks. First, they noticed that the safe and unsafe responses are indistinguishable based on the cost values alone. So if we just look at the cost value distribution, like this is a scatter plot of the cost values, you can notice that based on the cost or the reward values, right, it's really hard to distinguish which answers are safe and which answers are not safe. And this dotted line here is kind of the threshold between the two. So in other words, it's very hard to find a separation threshold, right, based on these cost values alone. So it's really difficult to do that if we want to fit a cost model according to, the claims in the paper and their experiments. So in order to resolve this, what they have considered is they thought a little bit about the problem, and then they changed the Bradley-Terry model to include additional terms, which we will discuss now. So they imagined, to think about this, right? They imagined the existence of a virtual response, which actually happens on the boundary between safe and unsafe regions, right? So between safe and unsafe regions, what we're going to do is we're going to imagine that there is a point y0 that is on the boundary, right, between the unsafe and safe. Now, because on the boundary, let's assume that the value of the cost of that y0 point is actually equal to 0, right? We're going to make that assumption. Why? Because y0 is an imaginary response which is actually sitting on the boundary. Now we have two cases. The first case is that if the response y is unsafe, meaning that s of y is equal to +1, then the cost model needs to prefer y over, y0, right? Why it needs to do that, we're going to shield against that, right? But we want a model that is going to be, preferring that so we can later on shield against it, right? So now the cost model will tend to prefer y. So the idea is that we would like to maximize y better than y0 given x. So now, what is the probability of y being better than y0 given x? Well, it's just the sigma of c theta yx minus c theta y0x. But notice that c theta of y0x is equal to 0, right, by our definition, meaning that now the probability of y being better than y0 given x, right, that is simply given by sigma of c theta of y and x, right? Okay. So now the idea here is that since s of y is equal to +1, that's my binary variable, then this is equal to that. So now you have sigma of sy c theta of y and x. But now you can consider, right, the second case where the y is actually safe, right? So sorry, this is a typo. In the second case, it should be if y is safe, not unsafe. This is unsafe, but now we consider the second case where if y is safe. So if y is safe, then s of y is equal to -1. That's by our definition on how we define this s of y. And now we would like the model to prefer y0, and i.e. we would like to maximize the probability of y0 to be better than y given x. Now, this will be the probability of y0 better than y given x as defined as the sigma of c theta y0 of x minus c theta of y of x. This is just following, like the Bradley-Terry model. And then c theta of y0 of x is equal to 0, as we showed here. And that would give me, at the end, sigma of s of y, c theta of y, and x. So now, if I can use these probabilities, right, additionally in my Bradley-Terry model, right, in order to fix that loss function, right, then I can encourage it to also find these thresholds that are separating things on the boundary. And that's exactly what they have done. So what they have done is to improve the performance, they introduce a new loss. And that new loss takes into account the harmless data set. It takes xj, yj win, and yj lose, but additionally, it takes these s win and s lose, which are either +1 or -1. The way they add this loss is really, very simple. They take the standard Bradley-Terry loss, right, which is maximizing the likelihood. That's what we tried to do before without finding the correct threshold. And now on top of that, we're going to add this loss that we have actually derived here, where we're talking about the sy multiplied by c theta and sy multiplied by c theta, where sy could be +1 or -1, depending if the response is safe or not safe. And now this will give us this additional loss where now you have the expectation from the data, the harmless data that you have, and then you have log of sigma of S win C theta Y win X plus log of sigma S lose C theta Y lose of X. So now this new loss, right, is kind of maximizing the likelihood to this threshold, which is this imaginary point Y0 that we have introduced. And this is kind of still a Bradley-Terry model, but it's kind of a modified Bradley-Terry model where the first loss is trying, just to maximize the standard likelihood, but then the second loss is trying to maximize the likelihood to the threshold. Why we think about it maximizing likelihood of a threshold, because it's actually derived from what we just described here, where we assumed we have this imaginary response, right, on the threshold, and we considered the two cases, and then we added these probabilities as part of my new loss. So now I have the standard loss, and then I have a new loss, which is maximizing the likelihood to the threshold, where we have this imaginary response Y0. Okay. Now, when they've done that, they actually fit the model, and now you can see very much better results, right? So you can see that before, without doing the Bradley-Terry modification they made, we couldn't really distinguish, between the safe and unsafe answers on this scatter plot. But now, after doing this fit, we can actually nicely make this distinguish between the two cost based on the cost values. And similarly, this happens in the distribution, right, where now after you do this trick that they had here, you are actually able to kind of separate these two distributions from each other. So now this model, right, that is based C theta, which is based on this loss, is a better separation. Is a better separation with respect to a threshold than, without including this imaginary response that belongs on the threshold. Okay. Now, okay, so imagine, right, for now I actually have done this, right? So I've actually, took the the helpful data set, and then I actually use the standard Bradley-Terry model, and then I fit the reward function, R phi star. And now imagine I take the harmless data set, and then I do the modified Bradley-Terry model, and I fit C theta star of X. Please notice I changed the notation a little bit to the paper because when I try to understand a paper, I try to rewrite the equations myself. So that's why maybe the notation is slightly different than what they have in the paper. And if you actually find any errors, please let me know in the comments below, and then I'll make sure to fix them. Right, so now we have these two models. One is a reward model and one is a cost model. Now, what is interesting, right, is now I don't want to find a policy that just maximizes my reward like the standard way I do in RLHF, right? Because in RLHF, I would find this reward model, and then I'll just do gradients, with respect to using PPO in order to maximize the rewards. But now, because I have this cost, I want to find the policy that is feasible with respect to this cost as well. So I want to maximize the reward, but I want to be safe. So I want to be feasible with respect to my costs, C theta star. So this is a pictorial depiction in a way. So if you have your policy space in RLHF, which is kind of your LLM that you will update based on the reward typically, you can get different policies depending on the PPO updates, right? However, what we are really looking for is not all these policies. We're only looking for the feasible set of policies that belong in what I depicted as the green circle here. So we want to find those policies that maximize the reward but are safe or are feasible with respect to this constraint C theta star of Y and X. So we want a policy that maximizes rewards but is also feasible with respect to constraints. So how do we do that? Well, what we're going to do now is we're going to generalize the notion of MDPs, right, in order to be able to handle this safety kind of constraint. So in standard RLHF, you would typically parameterize your policy by lambda, by some parameters vector lambda. So this would be your LLM, right? Policy LLM that you will do updates in the reward with standard RLHF. And you would actually use something like PPO, proximal policy optimization. But I also put natural actor critic here because I think PPO and TRPO are just derivatives of the natural actor critic, which has been proposed a long time ago. But in any case, what you are going to do now is you're going to maximize with respect to lambda, this expectation over your X coming from your data, prompts coming from your data. And then you have an LLM policy, which is parameterized by lambda. And now we use the reward model that we have fitted. So we do just PPO on that. So that was standard RLHF. Now in the constraint RLHF or the safe RLHF, what we are going to do is we're going to maximize with respect to lambda the expectation of the X coming from the data and the LLM policy with the reward. So this is the standard, right, RLHF strategy, where I find the policy that maximizes, right, my rewards. But please notice that we have now a constraint where we want to have the constraint satisfied. So this gives me the feasibility procedure. So I want subject to C theta star of Y and X to be less than 0. So this I want to be feasible with respect to that safe or constraint RLHF. Now, please notice that this constraint in this way, it is actually defined for every X from your data and for the Y coming from your policy, right? So this C theta, which is this constraint, I just rewrite it here, just to detail to you that this is a constraint for all X's and for Y that are coming from the policy, which is the LLM you're trying to fit. Now, the problem is that this is very hard problem to deal with, very hard constraint to deal with, because it has to hold for every X, right? And for Y coming from the policy. So rather than doing that, what we are going to do is we're going to consider a relaxed constraint MDP problem. So instead of saying we want it to hold for every X, right, and Y coming from pi lambda, what we're going to say is we're going to say that we want it to hold an expectation over X coming from my data and not for every X. So on average, I want this constraint to hold, and I want it to hold such that it's less than some D value, which is like a hyperparameter we are setting. So what really happened is that I went from the standard RLHF to a constraint RLHF by introducing my constraint model. I think this should be C theta star, but regardless of that, just assume you have a model. And now you said you wanted this to hold for every X and Y coming from your policy, but we said that that's hard because it has to hold for every X. So what we're going to do is we're going to further relax that, and then we're going to say we want the constraint to hold on average, right? So we want it to hold an expectation to be less than some parameter D, which we introduce. So this is a relaxed problem of the constraint problem, and that's what we typically do in RL, in constraint MDPs and constraint RL. So there is nothing weird, let's say, this paper is doing. This is a standard practice, more or less, in constraint MDPs. However, there's a way to improve this, as I will mention in the later part of the talk. And now, once you have this problem, now you notice that this problem becomes a standard constraint MDP problem, which you can solve using Lagrangian methods, right? So what we can do now is that we can transform this constraint MDP problem into an unconstrained problem by introducing the Lagrangian and then doing the dual formulation, i.e. following standard constraint optimization thinking. So instead of just doing max of this subject to the constraint, what we can do now is we can do a min-max problem where we try to minimize with respect to lambda the first loss plus the Lagrange multiplier is new, and then we have the constraint here. So all I've done here is I've just taken this rod, the Lagrangian, and now I have the dual problem. So here I have a min-max, and then there's an expectation of my first loss, which I'm interested in, which is this guy. And then I add to it a Lagrange multiplier with the constraint, and that's this guy. So again, there's nothing weird happening here, right? This is just standard constraint optimization that is going on. And in this video here, where I describe one of our works, I actually detail this procedure, how you would solve this. So if you're interested, please have a look at this video, which will tell you more about why this is true. But for now, all we need to know, right, is that we can transform a constraint problem into an unconstrained problem by writing the Lagrangian and following standard constraint optimization setup. So now you have min over lambda, the LLM policy parameters, max over nu being positive or equal to 0, the Lagrange multipliers, and then you take the first loss and add to it the Lagrange multiplier multiplied by the second loss. And now, in order to solve this problem, you can simply iterate, right? So you can, for example, do a gradient step in min lambda. So you do the gradient step in the LLM parameters, and then followed by another gradient step in the Lagrange multiplier parameters, right? So it's just solving a standard kind of a min-max problem now. Okay. And here are some of the experimental results. I'm not going to dig a lot into them. I would say maybe go to the paper and have a look at this. But here, what they are able to show that indeed, the method that they have used is capable of improving, this harmful ratio for different types of models like alpaca 7 billion, beaver v1, beaver v2, and beaver v3. So here they say that the 3 rounds of safe RLHF significantly improved the LO scores in both helpfulness and harmfulness, as evaluated by both GPT-4 and the human evaluators, right? So here they actually do two types of evaluations. One is based on a human, user case study, and one is based on GPT-4, where they actually ask GPT-4 to evaluate whether the response is safe, not safe, harmful, not harmful. And what is interesting is that in these two plots, you see that there is kind of an alignment between what GPT-4 says and what the human says in terms of the, helpfulness and harmfulness. But now what they're able to show is that we are able to show that a Beaver v3 model demonstrated an increased LO score for helpfulness and also an increased LO score for harmfulness. So in other words, what it was able to do is we decreased, the probability of harmful responses from 53%, which is very high, to only 2.45%, which is an excellent or cool, very cool result. And of course, please refer to the paper, to have a reading about more results. Now, the last thing I would like to mention is a low-hanging fruit research extension, which if you are interested in, we can definitely collaborate on. So notice that when they have had the relaxed problem, right, they actually considered the expectation, right? So they said on average, I want to go, from a cost on every X, right, to an expectation on, i.e. on average. Now, this is cool, right? But this is only guaranteeing on average safety, so to say. One way to extend this is you can become almost sure safe by considering different types of constraints. So instead of just collapsing for every X and Y, collapsing that cost into an expectation over your data, you can actually collapse that cost into a constraint, which is like a conditional value at risk constraint. So that will be like the probability of being safe. And then if you actually maximize this or deal with this constraint problem, then you will arrive at almost sure results, meaning that your results will be with a high probability safe rather just on average being safe. So we have a paper on this, and I think it's nicely applicable. I don't know how the results will look. We need to see, but it could be nicely applied to this problem where we just kind of replace the expectation with a CVAR constraint, and then our paper will get rid of the primal dual problem that this paper has considered, because the way it will work is by state augmentation. However, we can guarantee almost sure safety, and this could be an interesting extension. So if you really want to understand the potential drawbacks of the min-max kind of solution to this problem, in that video I referred to, and I will put a link to it in the comments below, I actually talk about the potential drawbacks of a min-max solution and propose an alternative. So the idea would be to try to combine that alternative, right, with a modified version of this constraint in order to get almost sure safety. In any case, I think this is an amazing and a fantastic paper. I think it got a spotlight talk in iClear, if I'm not mistaken. And I really think it's worth reading, looking into. And I'm very, very excited that actually, finally, we are starting to think a bit more principled about the problem of safety and human alignment when it comes to large language models. Because these constraint MDPs, they offer us a very nice principled manner to get a feasible policy where we have, a reward and subject to certain constraints. We also ended the video with an idea of a future extension. I hope that, that could help somebody if they are interested in it. And if you are, please let me know, write me. I'll be very happy and excited to work together with you on this. And with that, I would like to end it. I think this was really an awesome paper, and I will see you very soon again. So thank you so much. Please make sure to read the paper. Cheers.